Today we're going to talk about Star Watch, about the winter sky and how full of wonders it is. We're going to talk with Frank Petrie, the president of the Battle Point Astronomical Association. And this is the Something to Talk About program that we do here at the Senior Community Center at least 3 times a week, although it's a holiday week, so I guess not every week. And it is sponsored by the great folks at Fieldstone Communities. They offer innovative and compassionate care up on Rolling Bay, and they are accepting residents. They have day stay and respite programs to find out about. To learn more, call 360-689-4314, and you can schedule a tour. Also, I'd like to acknowledge that this meeting is on the ancestral homelands of the Coast Salish people, specifically the Suquamish tribe, our good neighbors who are the people of the clear salt water, and they are very hospitable. We are grateful for their hospitality, and also we honor their heritage as environmental stewards. Anne Lovejoy is here to get us started and introduce Frank to us.
Thank you, Reed. So, Frank, you are the president this year, right, of the Battle Point Observatory. And I thought it was great that just the other day you had a whole busload of seniors from the senior center there. What kinds of things were they interested in? What were you telling them?
Well, we talked about a little bit about the observatory, and we talked a little bit about, I think we covered what's up in the sky, but I'm not sure, but I'm going to do that today. And then we got into discussing the James Webb Space Telescope. So it was very, very good.
Yeah, that's some of the incredible images coming out of that telescope. I hoped you'd be able to tell us a little bit about that.
Yeah, I'm going to actually change my name here. I should have done this earlier. It says BPAA, but I'm adding my first and last name.
All right. So we know who you are.
Okay, so shall I get started?
Sure. If you want to start, maybe let's talk a little about the night sky in the winter. I think a lot of people don't, it's often cloudy, maybe it's hard to see, but there's some crazy cool stuff out there, right?
There is quite a bit. And I've got some slides to show that I'll get to here in a minute. How much time do I have?
An hour.
Okay. All right. I'll try to move fast through my slides. But I'll cover quite a bit about what's in the sky and how to find your way around the sky when you go out and look up, because people are often confused. They go out and they look up and what the heck am I seeing? What's that bright thing over there? And so I'll explain all of that.
Great.
Okay, so shall I get started?
Sure.
Okay, I'm going to share my screen. And so now you can see, and I'll launch the slideshow. So here we are. So thanks, Anne and Reed, for the introduction, and welcome everybody. So I want to introduce you to welcome you to the Battle Point Astronomical Association. Here's a picture of our observatory in Battle Point Park. This is the Helix building. We operate out of this building, which is a relic from World War II that was slated for demolition, but the club founders, Ed Ritchie, John Rudolph, and Mack Gardner, convinced the park department to save the building and let them put an observatory in it. So we put I should say, this was before my time, but they put the dome on the roof and made all the improvements inside so that it can be used as an astronomical observatory on Bainbridge Island. And this is the telescope that's up inside that dome. This is the 27.5-inch Ritchie telescope. It was built around a 27.5-inch parabolic mirror that was donated to our organization by Boeing. The mirror was left over from the Star Wars program back in the 80s, and we took delivery of it in the early 90s. And then Ed spent the next year and a half refiguring the parabolic shape to make it suitable for this telescope. Meanwhile, they purchased the materials and built this telescope tube from scratch. This is not something you can buy off the shelf. This is a homemade telescope. And It has, up here you can see it has about 108-inch focal length, which translates into about an f4, f3.9. So if all of you photographers out there, you know what this means. It's a computer-controlled equatorial telescope, meaning it rotates about an axis that points at the North Star so that it tracks along the equator. And then it can be pointed up and down using this big gear, this big gold gear here on the side. And we use it now for astronomical imaging. It is capable of visual observing, but we find that we can better accommodate our visitors using our smaller telescopes for visual observing, and we have dedicated this telescope to astrophotography. And here's a couple of pictures that we've taken with it. We have the planet Jupiter here in the middle. It's still kind of a fuzzy picture. We're working on dialing in the telescope to get the image is much more crisp. The other factor we're dealing with is that the skies above Bainbridge Island aren't entirely suited for astrophotography, but there are ways to work around that, and we're developing those methods. Next to it here on the left is the Horsehead Nebula, which is a nebula in the constellation Orion, and it's quite a famous nebula. It has a whole story in and of itself, but I don't have time to get into that here. But anyway, you can see that we are able to capture some pretty amazing deep sky objects with this telescope. We also operate the John Rudolph Planetarium. This is our meeting room downstairs, and the dome that you see up over the top is the planetarium dome. And we used to have a projector that shined up onto the bottom of that dome and projected images of the night sky so that you could have a real planetarium experience. That projector died a few years back, and we have now ordered a replacement projector for that. And I've kind of overlaid an image onto here. In the middle here, you can see what the new projector would look like. This is a demonstration model, but we've ordered our new projector, and we're raising funds to pay for that projector. So we certainly welcome donations from anyone. And if you want to support our effort to get this new projector and get the planetarium back in operation, that would be greatly appreciated. But up on the dome, this was a demonstration, and the fellow who gave the demonstration had some 3D photography, 360-degree photography of some places in Egypt, and so that's what you're seeing here on the dome. It's much better to show the night sky up there. Okay, and just a quick mention of our partners. We have a strong relationship with KiddieMU. We've done some work with them at the Kids Museum, Kids Discovery Museum, and they have come out to the observatory and hosted some day camps and things, science day camps, and we've helped them with that. So we are excited about our future working with KiddieMU. And then these other organizations represented here are organizations that provide funding to us. In particular, the Bainbridge Community Foundation recently gave us a community grant that is going toward the purchase of the planetarium. So we're almost there with having the money that we need to complete that purchase. Okay, so here's the night sky. When you go out and you look up, what do you see? You see a lot of stars, and it's kind of confusing. You don't know what you're looking at. So this is a screenshot from a program called Stellarium, which I'll talk about in a little bit, and it's looking north. This is the directions here on the horizon. We got the horizon down here. Up at the top, this little green cross with the Z, that's the zenith. So imagine that's directly over your head. If we were in the planetarium, you would see this, the horizon would be where the horizon belongs, and the zenith would be up over your head. But on a flat screen, of course, we can't do that. And so what do you see here? Well, the first thing you'll notice when you look north is the Big Dipper. And right now, this time of year, the Big Dipper is low in the northern horizon. And so you want to look low in the north and you'll see the Big Dipper. And the Big Dipper is made up of 7 stars in the handle. There's 4 stars in the handle, and then there's 3 more stars that form the bowl. And these 2 stars on the right-hand side are pointing up, and they're called the pointers because they point at Polaris, the North Star. And Polaris is also the pole star. The whole sky revolves around Polaris. So over the course of the evening, new sky will rise in the east and go over your head and go across, and then it will set in the west. And the Big Dipper will rotate around Polaris over the course of the evening. Yeah, the Big Dipper never sets. It's an example of a constellation that's called circumpolar, which means it goes around the pole and never sets. We always can see the Big Dipper. Now, Polaris, of course, is part of another asterism, which is called the Little Dipper. And so you can see that here. And the Little Dipper is made up of mostly dim stars. But if you can see it in a dark enough sky, it looks like it's pouring into the Big Dipper. So the Little Dipper is pouring into the Big Dipper. Now, another thing you can look at is if you look across from the Big Dipper toward through Polaris and over to the other side of the sky, about equidistant, you'll see another asterism up here, and you can't really tell what it is, but it's Cassiopeia.
Okay.
So once you get out in the night sky and you start identifying these very prominent shapes in the sky, you can start to get your bearings and figure out where you are and what you're looking at. Now, one more thing that you can see here, rising in the east, is the Pleiades. That's the little star cluster over here, is the Pleiades. And at this time of the evening, this is about 6:15 this evening, this is what you'll see. Orion will not have risen yet. And we'll talk about Orion in a little bit. Okay, now if you spin around and look, whoops, what happens? If you spin around and look to the south, here again, you see a bunch of stars. You see some bright stars. If you're lucky and the sky is dark enough, you might even catch the Milky Way glowing up through the sky. It's hard to see here from Bainbridge Island, both because of light pollution and also because our skies are not super crispy clear. There's a lot of moisture in the air, and that tends to wash out what we can see and reflect the light pollution. So it kind of hides things. But anyway, you can see some really bright objects here. For example, this one here is the planet Jupiter. And that's really the brightest thing in the sky right now. So if you go up and you look to the southeast, and you see that very bright light in the sky, that's Jupiter. And down to its right and a little bit lower is the planet Saturn, this bright one here. Saturn is much dimmer than Jupiter right now, but it's also quite obvious. And they're the kind of the first 2 things you'll see as the sky darkens in the evening, which these days is about 4:30, 4:45. There are 3 other bright stars that you'll see in the sky. There's the star Vega in the constellation Lyra, the harp. There's Deneb, which is in the constellation Cygnus, the swan, and Altair in Aquila, the eagle. And these 3 stars, even though they're in 3 different constellations, form a famous asterism called the Summer Triangle. And you can see that the Summer Triangle is quite obvious. It's called the Summer Triangle because it's up all night in the summertime, but this time of year, as the sky darkens, it's already dropping down toward the west. And soon, as we move around the sun in our orbit, the summer triangle won't be visible at all as we get into winter. So these next couple of weeks are a good opportunity to get out and say goodbye to the summer triangle. Okay, let's see, what else have we got? Oh, here's another asterism, the Great Square of Pegasus. And this is another very obvious thing that you can see when you get out and look to the southeast. It's right above Jupiter right now. And that will lead to some other interesting things, which I'll explain here. Now, these images that I'm using are screenshots from a program called Stellarium. And here's a screenshot from Stellarium showing all the constellation lines. So over here, you can see Vega, Cygnus, and Altair, which form the summer triangle. Here's Pegasus. The entire constellation of Pegasus includes 3 of the stars of the square. The 4th star of the square, Alpheratz, is actually part of Andromeda. And another interesting thing is that in a really dark sky, you can see between Pegasus and up here is Cassiopeia. Remember, I showed you Cassiopeia a couple of slides ago. You can see in the east. But if you go between the square of Pegasus and Cassiopeia, you can find a very faint fuzzy right in here. I didn't highlight it for you, but that's the Andromeda Galaxy. And when the sky is dark enough, you can just catch a glimpse of it with your naked eye, but you can see it in a telescope as well. The Andromeda Galaxy is the largest galaxy that's nearby the Milky Way. It's about 2.5 million light years away, 2.5 million light years. So it's quite far away, but it's close enough that the Andromeda Galaxy and the Milky Way galaxy are actually interacting gravitationally. And in several billion years, they will actually merge together and become one galaxy. So that's another little interesting tidbit. Okay, now what I'd like to do at this point is switch over to, let's see how can I do this? I want to switch over to Stellarium itself, if I can do that without, oops, what happened? Nope, that's not the slide I want. I'm going to, all right, so it's not doing what I thought it would do. So I'm going to stop the share momentarily, and I'm going to, oops, I know what happened. I'm going to go to Stellarium. Okay, here we are. And I'll share my screen again. And this is the program Stellarium. We'll make it fill the screen. And now this is a live view of what I was showing you. Down here, you can see, I don't know if you can see, but these seconds are clicking away here. This is about 6:30 this evening. And here's Pegasus, Vega, Deneb, and Altair. And if I move forward in time, you can see the sky moving. I'm going to stop it there. I've got a little enthusiastic here. I want to be about 120 degrees field of view. So here's Jupiter. This green line is the meridian. That's a line that goes from the south, from this direction south. It goes up over your head and comes down into the north. And the zenith, of course, is right there on the meridian. And so as you watch, the sky rises in the east, so stars and constellations and planets rise in the east. They get it to their highest point when they cross the meridian, and then they drop down to the west and they set. So that's pretty much how the sky works. Now with Stellarium, I can move around the sky and see things. let's zoom out a little bit more. So here's the great square of Pegasus is right here. Here's Cassiopeia. And right here is where I showed you the Andromeda Galaxy. And if I zoom in a little bit more, come down. I hope you're seeing this pretty well on your screens. I know there's some latency involved with Zoom.
Oh, it's great. It's working great. It's fascinating.
Okay, so as I zoom in, you can see the Andromeda Galaxy here starting to come into view. And I want to center on that so that I can zoom in and show you. There's the Andromeda Galaxy.
Oh,
See that?
yeah, that's awesome. Wow.
Yeah, so this program, Stellarium, is quite powerful, and it enables you to do a lot of things and explore the sky, even when it's cloudy and rainy outside. And we'll be able to project this kinds of stuff on our planetarium dome once we get the new projector. So we're real excited about that.
When do you think that will happen, Frank?
We hope by early 2023. So maybe January, February, start watching our website for announcements about the reopening of the John Rudolph Planetarium.
Oh, great.
Okay, so let's see. The other thing I wanted to show you is that now here's the time. Can you read the time down here at the bottom of the screen?
Kind of small. Yeah, I can see it.
Okay, well, there's another, I can pop this up, and here's the date and time. I'll move this over to the other side so it's out of the way. But you can see that it's November 21st, and it's about 8:30 in this evening. And now you can see Orion just starting to rise. Mm-hmm. And as I go forward in time, speed up time a little bit, you can see Orion rising. And I'm going to stop it there. Now, remember I mentioned, I'll set this up out of the way. Remember I mentioned Jupiter here, and Saturn, of course, has gone off the screen. But there's another planet up here. There's Mars is up here right above Orion. So it's really interesting. It's a lot of stuff to see in the sky if you stay up late. This time, this is about 10:30, coming up on 10:30. Orion will start to be visible in the southeast. And of course, Orion's belt is here, and Orion's sword hangs down here. It's kind of hard to see, but if I zoom in, you can see that what we call Orion's sword is this bit that hangs down below. And that's the Orion Nebula. And actually several different nebulas are together in there. Let's focus on that one. Center on that. Now I can zoom in, and we zoom way in, and there's several different nebulas in here that you can look at. And these are quite stunning in the telescope.
Oh, you can see this well with that telescope?
Well, you can, and if the sky is really, really clear, you can get a hint of the color, and you can see that it's a smudge. And then when we get the camera fired up, we can take images, and we can get these of course are images from professional telescopes. And so we're working to try to get images as good as these. But that's our goal in life. And somewhere in here, I can't remember exactly where it is, but the Horsehead Nebula that I showed you is hiding in here somewhere. If I had more time, I could hunt for it and show that to you. So anyway, that's pretty spectacular.
Yeah,
now,
it is.
If you follow the 3 stars of Orion's belt and extend them down, you'll see the bright star Sirius starting to rise. And Sirius is the brightest star anywhere in the sky. It's the only things brighter than it are some of the planets. Jupiter gets brighter than Sirius. Mars will get brighter than Sirius. Venus certainly gets brighter than Sirius. But as we advance in time, you can see that Sirius is rising let's see, I gotta stop that. There we go. So now you can see Sirius is rising and Orion is getting higher in the sky. I'll zoom out a little bit so you can get the full picture.
This is amazing software.
Yeah, this is great software. How are we doing on time? I should move on.
Okay.
We're coming up on about a half an hour, and I've got a lot more I want to tell you about today. So
Let's go.
yeah. So one more thing I wanted to show you is that there is, the Earth goes around the sun. And because the Earth is tilted on its axis, sometimes the sun is high in the sky and sometimes the sun is low in the sky. And when it's low in the sky, it's winter time. And when it's high in the sky, of course, it's summertime. And that path that the sun takes, that the sun appears to take around the sky, is called the ecliptic. And this orange line is the ecliptic. And so when it's winter time, the sun is really low in the sky. And what that means is that when it's nighttime for us, look at the time we've got, it's about 1 o'clock in the morning right now. Because the sun is low, but it's behind us, the ecliptic is high in the night sky around midnight. And so this is a really good time to see some interesting things that live along the ecliptic. And of course, because the solar system is in the shape of a disk, the path that the sun follows around the sky, from our perspective, is the same as the path that all the planets follow around the sky, because they're all in a disk. And so the place to find the planets is along the ecliptic. Here's Jupiter down here. Here's Mars up here. Let's see, if I go backwards in time, let's go backwards in time.
You know, that makes total sense. And in my whole life, I never actually thought about it like that.
Yeah.
Of course they are.
Yeah. So here's Saturn. You see Saturn's on the ecliptic.
Yeah.
Jupiter's on the ecliptic, and we just lost Mars. Where'd Mars go? There's Mars. So now you can see this ecliptic. And if I zoom in a little bit more, will it pop up? Here's Uranus. It's too dim to see with the naked eye, but I've seen it in a telescope, and it's a little blue dot. So there's Uranus. And oh, look, here's the Pleiades.
Yeah.
Right, and Neptune and Pluto, Venus and Mercury, all are viewed on the ecliptic. And so the ecliptic has taken a very special meaning in astronomy ever since the time of the Babylonians. And it was way back then that the Babylonians noticed that the planets move differently from all the other stars in the sky, and they identified this pathway and they gave it special meaning. It had the constellations that live along this pathway were imbued with special powers. And so if you look at what they are, you can start to recognize some names here: Aquarius, Pisces, Taurus, Gemini. These are constellations that you recognize from something else, don't you?
Yes, we do, right?
They're the constellations of the horoscope, the zodiac.
Right.
So this pathway that lies along the ecliptic is of course called the zodiac, and all those constellations have historically had very special meaning. Nowadays, not so much to astronomers, other than they define the path of the sun and the planets through the sky. Also the moon. It's a new moon right now, so we can't see the moon on this particular screen. But if I, let's go backwards. It was just not too long ago that I'm going to go backwards a day at a time here. Let's see, here comes the moon coming backwards,
Yep.
see? And
Yeah.
the moon also follows the ecliptic. The moon's orbit is inclined slightly to the Earth's orbit. So sometimes the moon is south of the ecliptic, sometimes it's north of the ecliptic. Here it is waxing, and coming more and more full. You may have noticed the full moon this time around was really far north.
Yeah.
It's because of the orientation of the moon's orbit compared to the Earth's orbit. So anyway, okay, moving on. At this point, do you have any questions about anything?
You know, this might be silly, but what's the difference between asterism and constellation?
Constellations are recognized, well, asterisms are smaller patterns in the sky. Constellations are recognized in the mythology. Asterisms, not so much. Asterisms are more for the benefit of recognizing smaller patterns. What I can do here, down here, there's a little button I can push, which provides the constellation art.
Oh,
And
look at that.
Here are the mythological creatures, people and creatures that inhabit the sky. And so all of the constellations are identified, are associated with these figures. The other thing that more modern astronomers have done, have divided up the sky with boundaries so that each constellation has specific boundaries that, so that the entire sky, everything in the sky can be associated with a constellation, even though an object may not be part of the stick figure that we're familiar with. If there's a star in Perseus or a galaxy or something in Perseus, for example, and we zoom in, even though it's not part of the actual stick figure, all these stars are considered to be part of Perseus because they're within these red boundaries for Perseus or Taurus or Aries and so forth. So that's how astronomers have divided up the sky. So we can make that go away. There's a whole lot here. I could I could talk for weeks on this stuff.
I have a question. Can I?
Yes.
How
Sure.
many total constellations are there? And were these named? Like how long have they been sort of
Yes.
settled in the sky
Yeah.
and named?
How long have they had these names? Well, the Greeks, most of the constellations that we have names for come from the Greek and Roman mythology. And so you can find the stories of Pegasus and Andromeda and Cassiopeia in Greek and Roman mythology. And the Greeks and Romans, of course, were they lived in the northern hemisphere, and so they were most familiar with the constellations in the north. When mariners started to sail south, they discovered a whole new sky that was previously unknown, and they cataloged what they were seeing. And astronomers from England, for example, and Europe would travel to South Africa, and they would map the stars down there. And they created a whole bunch of new constellations. So there's a lot of constellations in the southern hemisphere that have more modern names, like like the Southern Cross, Crooks, and there's something called the ship's rudder. I forget the name of that. We can actually, well, I'm not going to do it now because it means resetting my software, but Stellarium actually does provide a view of the southern hemisphere as well. Actually, I know what I can do. If I go like this and I zoom out.
Oh, there you go.
You can see the entire sky.
Yeah.
With the Earth in the way. Okay. Now I can go here and I can make the Earth go away.
Oh.
And now you can see, it's kind of goofy, but so Vela, the sail, Sextans, the sextant. What are some
Frank, did those constellations have names that the native people in those countries had given them already? Is there any movement to reclaim some of that? Or
That's an excellent question. And the answer is yes, they must have had names. For example, the Polynesians were sailing and using their form of celestial navigation to inhabit the entire Pacific. And And so they had names for all of these. In fact, you know, I can select the constellation art for some of these. You know, here's Dorado, the dolphin fish. There's another one. There's one called, oh, I can't think of it. But anyway, so there's a setting in Stellarium. I have to dig down into the menu, but you can switch from these traditional Western constellation art and look at some more traditional art. And so that is possible.
So maybe we need a field trip when you get set up for the senior center to come back
Yes,
again and look at that.
Absolutely. Absolutely.
Planetarium.
We will definitely do that and have a planetarium show on that very topic. Okay.
It sounds like you could do a number of planetarium shows, right?
Oh yeah. Oh
like
yeah.
You could come 2 or 3 times and see a different topic, right?
Absolutely.
Oh, I love this.
Absolutely. And that's why one of the things we're excited about with our partnership with Kitty Mew is they can't wait for us to start being able to offer these kinds of programs for the kids to come and start learning a whole lot about the sky. Okay, sorry for making you dizzy here, but this is so much fun to scroll around through these. Okay, what I'm going to do now is leave Stellarium. Let's see, I want to do this one. And then I'm going to go back to my slideshow. And so here's where we left off. I'm back now in my my PowerPoint. Hopefully it will work. And so Stellarium, write that name down. It's planetarium software and it's available as a free download. If you Google Stellarium, it'll take you to the website where you can download, and they have versions for Mac and versions for PC. And if you go to the App Store or the Android store, you can find the apps for your phone and your iPad and your tablet. I think you have to pay a little bit on the App Store to get the Stellarium app. But if you download the desktop version, which is what I'm showing you today, that's entirely free. And there's a bit of a learning curve with it, but if you are interested, just give me a holler and I can certainly help you with that. Okay, so moving along, the other thing I wanted to talk about today, if I can get my slides to advance. One last thing here, some upcoming meteor showers. Unfortunately, just a week or so ago, we missed a meteor shower, the Leonids, I think it was.
Yes.
And I did talk to someone who tried to see some meteors, but there wasn't much to see. You need a really dark sky. But coming up here later here in November, right around just after Thanksgiving, we've got the Andromeda meteor shower, which is not very impressive. But if you look toward the south, you might catch some of those. In December, we have the Geminid meteor shower. This one potentially could be very good. So put December 13, 14 on your calendar. The important thing about looking for meteors is that it's best to look after midnight. And the reason for that is, if you think about it, the Earth is going around the sun, but the Earth is also turning on its axis. And when it's daytime, we're facing the sun, obviously. So we're not on the front side of the Earth. And as the Earth turns at sunset, we're on the back side. We're looking out the rear window of the car. And then as the Earth rotates around to midnight, we're looking out away from the sun. And then as the Earth rotates toward dawn, we're actually on the front-facing side of the Earth. In other words, we're looking out the windshield. And what do you know about the windshield on a car moving down the highway? That's where all the bugs get splattered, right? That's where the raindrops hit the hardest. And that's why we see more meteors in the hours between midnight and dawn than any other time at night. So if you really want to see meteors, that's the time to do it. It is possible to see some in the early and mid-evening, but the best time is after midnight. Okay, moving along. I did want to talk about the Webb telescope, and I'm not sure we're going to have a lot of time to get through this, but if you've seen you've seen news reports about the Webb telescope, I'll try to tell you what it's all about. The Webb telescope is a very sophisticated telescope that was launched in space about a year ago, just about a year ago, Christmas Day, 2021. It has 4 science objectives. It's going to study the early universe. It's going to study the evolution of galaxies over time. It's going to study stellar life cycle, the life cycles of stars, and it's going to study other worlds, not only the other planets in the solar system, but also planets around other stars. And so these are the 4 main science objectives. It's deployed at a place called L2, the Lagrangian point number 2, L2. Here's a picture of the launch on Christmas Day from the spaceport. The European Space Agency has a spaceport in French Guiana, the northeast coast of South America, and that's where Webb was launched from. Shortly after launch, when it left the atmosphere, the nose cone was jettisoned, and revealing the telescope all folded up origami-like inside. And then the telescope was then slowly opened up. It was a deployment sequence that's shown here. I won't spend a lot of time on this, but as it was traversing its distance from Earth past the orbit of the moon here and out to the Lagrangian point, L2. Excuse me. The telescope unfolded, the sun shield unfolded, the mirror unfolded, and it slowly turned on all the equipment, and it became operational. It took about 6 months to get it fully operational, and in July of this year, it started sending back images. Here's a diagram of L2. There are 5 special points in any. As the Earth goes around the sun, the gravitational interaction between the Earth and the sun results in these 5 special points. 5 special points. So L1 is a balance point between Earth and sun, where the gravity exactly balances. L2 is on the other side of that line, and it's a point where the combined gravity of Earth and sun is counterbalanced by the centrifugal force of the Earth going and the object at L2 going around the sun. So there's some centrifugal force wanting to pull it out versus the gravitational force wanting to pull it in. So there's a balance point there. L4 and L5 lead and follow the Earth by 60 degrees. And those are areas where space debris collects, like asteroids and things will collect in these points. And then, I missed L3, which is all the way over here on the other side of the sun. So anyway, those are the Lagrange points. And Webb telescope is out here at L2. And it doesn't sit at L2, but it orbits L2, goes around and around. The telescope itself has several instruments. There's 4 major instruments: the NIRCam or near infrared camera, the near infrared spectrometer, the mid-infrared instrument, which is a camera and spectrometer combined, and then something called the fine guidance sensor and near infrared slitless spectrograph. So these are the 4 main instruments on Webb. And spectroscopy is a major feature. The telescope is tuned to observe in the infrared. It looks for infrared light, not visible light. The Hubble telescope looks at visible light. Webb looks at infrared light, which is longer wavelengths. And it uses spectroscopy as well as imaging to study that light. So here's a quick tutorial on spectroscopy. You know that when you shine light through a prism, you get the rainbow. The light is refracted in the colors of the rainbow. And what's shown here is the visible spectrum. But beyond the red, there's also the infrared, which we can't see with our eyes, but Webb telescope can see what's going on up here. And if the light source, before it hits the prism, if it hits the prism directly, then you get a full spectrum. But if the light source shines through a gas cloud, then it hits the prism, the spectrum, there will be gaps in the spectrum. There'll be black lines appearing in the spectrum because the material that's in that gas cloud will selectively absorb certain wavelengths of light. And so you won't see those wavelengths when you look at the spectrum. And the location of the black lines correlates exactly to what kind of material is in the gas cloud. So we can identify the material in a star or in a nebula by the black lines that appear in the spectrum. Similarly, if there's a gas cloud that is energized by some whether there might be a star inside of it or there might be some chemistry going on that causes it to be energized, then it will emit bright lines corresponding to the material that's in that gas cloud. And so we use what's called absorption spectra and emission spectra to identify the material that's in stellar objects. And here's a periodic table. You may remember this shape from your high school chemistry, but instead of talking about the numbers of protons and neutrons and electrons in the various elements, this periodic table is showing you the colors of light that's emitted and absorbed characteristically by each of the elements. And so these spectra are like fingerprints. You can tell what elements are present by the lines that appear in the spectrum. And so what Webb will do is it will take light from a distant object, it'll run it through those instruments, and it will generate spectra, which are then transmitted back to Earth. And in those different spectra, we can identify different elements. Carbon, nitrogen, oxygen, iron are shown here, but we can see not only atomic elements, but we can also see molecules. Certain molecules have certain spectra as well. So they're like fingerprints. And that's really the basis for the science that the Webb telescope will be doing. So here's the first image that was released back in July. It's a deep field showing a cluster of galaxies. Well, actually, these bright objects with the diffraction spikes, those are stars in the near foreground. Those are stars that we see here in the Milky Way. But we're looking through those, and beyond them, there's this cluster of galaxies. These big, bright blobs are middle ground galaxies, and far beyond them are all these other tiny little galaxies that you can see in these pictures. And there's thousands of them, all different sizes. And some of them are directly behind this mid-ground blob, and the light from those distant galaxies back here is being refracted or bent by the gravity of the foreground cluster of galaxies, so that when we see that light here on Earth, it looks like that light source, instead of being back here, it looks like it's up here and it looks like it's down here. And this is the bending of light by gravity. And that allows us to see these background galaxies, and they're smeared out in arcs because of the nature of the gravitational lensing that's going on. These are called Einstein arcs because the bending of light was predicted by Einstein in the theory of relativity. And so if you study this picture, you can see there's a lot of little arcs in here, and those are all background galaxies that are being refracted or lensed by the mass of this intervening cluster of galaxies here. And if we take a closer look at part of this, we see there's an arc here and an arc down here, and they've run those through the spectrograph, and they see that the spectrum of both of those arcs are identical with hydrogen and oxygen and some other stuff. But because of the close match between these two spectra, we know that those two arcs are coming from the same background galaxy that's hiding behind this bright cluster. So that's the power of spectroscopy. That's an example. Here's another example. We have in this image, they've identified 4 little galaxies, tiny little galaxies, but they've zoomed in on those. And the first one here has these elements are showing up in this particular pattern. And if we look at this next one, we see those same features, but they're shifted to longer wavelengths. And on this one, they're shifted even farther. And on this one, they're shifted farther still. And this shift of these identifiable features in the spectra of these objects is called a redshift. And the redshift correlates to distance. And so we know that this galaxy, because of the position of these spectral features, we know that this galaxy is 11.3 billion light years away, and it's, to put it another way, we're seeing it as it was 11.3 billion years ago. And this one is 12.6 billion light years away, 13 billion light years away, 13.1 billion light years away. Now, astrophysicists know that the universe itself is 13.8 billion years old. And so what we're seeing here are galaxies very near to the beginning of the universe, to the birth of the universe in the Big Bang.
That's incredible.
Yeah, it's very incredible. Now
It's incredible.
here's some more detail on this one that's 13.1 billion years away, a billion years old. I should say billion years young, because it's really, we're seeing it at a younger time.
Right.
So this little galaxy, they've done this detailed spectrum, and they've identified the oxygen, hydrogen, neon in the spectrum of this galaxy. So that tells us that even way back then, the chemistry that we know and love here on Earth was pretty much the same. Which validates a fundamental assumption that astronomical science is based on, which is that no matter where we look, everything, all the same laws and rules of physics apply, even far off in the distant past and far, far away. All right, here's another look. This is a more recent image that came from Webb. And of course, here's the stars with their diffraction spikes, and here's a bunch of galaxies. And they've identified 2 particular galaxies. This one here with the box around it named called 1, and over here there's another one called galaxy number 2. And galaxy number 1 has a redshift of 10.5, which correlates to an age. Let's see, it's about what is it? This galaxy existed. We're seeing it as it was 450 million years after the Big Bang. So that's a very short time after the Big Bang. And then this one, number 2, has a redshift of 12.5. So it's even farther away. And we're seeing it as it was only 350 million years after the Big Bang. So Webb is showing us things we never expected to be able to see these things, even in the Webb telescope. The surprise here is that galaxies from this early in the universe are as bright as they are. We're seeing them because they're bright, and we didn't expect them to be bright like this. And so we didn't expect to see any of this. And so the presence of these highly redshifted galaxies in Webb images is giving us new information about the early universe that we did not expect. So you can look forward to a lot more pretty amazing scientific results coming out of these studies. Now, I want to point out that this is 2 parts of one image here, this wide image that we're looking at here. They kind of cut it in the middle so they can show the galaxies, but they give a scale bar down here. This is 40 seconds of arc. 40 seconds of arc So 1 second is, of course, 1/60th of a minute of arc, and 1 minute of arc is 1/60th of a degree. So what we're looking at here is a very small part of a degree. 1 second of arc is 3,600, 3,600. 60 times 60 is 3,600. So 1 second of arc is 1/3600th of a degree. It's a very tiny, tiny thing. And this is 40 of those tiny things, this scale here on this image. So I put together a little thing here that shows you that if this image that you're seeing on your screen right now was overlaid on the moon that is about 30 minutes of arc. And so it looks like this. Here's the moon to scale, and here's that image to the same scale. And so this tells you that the area of space that Webb is looking at is this very tiny little image of space. If you were to look out on the sky, this would be, I mean, you know how big the moon is when you look at it. It's fairly big, but this is a very tiny part of the moon. And that Webb is able to see these kinds of details in that tiny, tiny bit of space is just pretty amazing.
It is amazing. Frank, we're getting close to the end of our time, but what else, anything particular you want to make sure you tell us?
Well, okay, so let me scroll through my slides. You're all going to have to come back.
Yeah, we definitely are going to have to come back.
I want to show you, so Webb is looking at, of course, galaxies and stars and things, but I want to show you this slide here. Can I get to it? So Webb is also going to be studying exoplanets, and the way it will do that is, this is a cartoon image here. This is a star, this big orange ball, and here's a planet passing in front of the star. So it shows it coming into the star and passing in front of it between us and the star, and then passing out. And so we're tracking this in this spectrum here, we're tracking the brightness of the starlight. And then as the planet passes in front of it, the starlight dims by a very small, this is like 1% here. It's from 99 to 100, or from 100 down to 99%, a little less than 99%. So it's a very small change in the brightness of the starlight. But as the planet passes in front, we see this dip, and then we see it come back up again as the planet moves away. And as it ramps down and then ramps back up, what's happening here is that we're seeing the starlight shining through the atmosphere of the planet. And as we look at that light shining through the atmosphere of the planet, we can do spectroscopy. And here's a spectrum that's showing the presence of water, H2O, common water, in the atmosphere of that planet. It's the planet is called WASP 96b, and we're seeing water in its atmosphere, which is pretty freaking amazing.
Yes.
There's another look at that. Here's the same. Oh wait, this is 39b, a different planet. But you can see that as the starlight dips, we can see that some elements, there's different wavelengths are being reduced by differing amounts. That's why these are not all in a line here, but the red ones are up high, the blue ones in the middle, and the green ones down below. And so what we're seeing is that more of these green ones correspond to, well, okay, so some of the light is being blocked more than other light. Different wavelengths of light are blocked by differing amounts. And this pattern is characteristic of the presence of carbon dioxide in the atmosphere of this particular planet. So we're able to discern that kind of detail. And again, here's another version of the spectrum that shows a very strong carbon dioxide feature in the spectrum of this planet. So that's how Webb is going to help us understand details about what's going on exoplanets. And a few months ago, we had a talk at BPAA by Natalie Allen. I don't know if you may recognize her name. She's a graduate of Bainbridge High School, class of 2016. she's now at Johns Hopkins University, and she's on the front line of these kinds of studies. Her office is right across the street from the Space Telescope Science Institute in Baltimore. And so she's right there at the cutting edge of these kinds of studies, and is very excited. She gave a talk to us, as I said, a few months ago, and was very excited about the upcoming results. They're going to be releasing many papers, research papers, describing what they're finding on these exoplanets. I have more to show you, but looking at the time, I'm going to jump to the end. Say thank you. And does anybody have any questions before we go?
I have one.
Uh-huh.
The chart that has all the elements on it and then has, you know, the light refracted, is that possible to get? There's a young man I know. I mean,
Yeah.
he's young, but I gave him a book of elements, and he's memorized them all this year. I gave it to him for Christmas, and so I'm looking for something to go with that. So I just didn't know if there was a chart or something.
Yeah, there absolutely is. I can send Anne a web link to
Okay.
where you can find that image, as well as explanation of what it means. And you can refer that, you can send that to him, and
Okay.
he can go to town on that.
Yeah, exactly. That'll keep him busy. I'll send it to his mom.
Yeah.
Will be
Yeah. Okay. Yeah. I'll send that link to Anne.
Yeah, that'd be
Okay.
great. I would love it too. I just think, you
Yeah.
know, my granddaughter's really interested in this stuff, and I can't wait.
Yes.
We're going to bring our grandkids to see some of your planetarium shows and stuff.
Yeah.
And I think we're going to bring busloads of seniors too,
Yeah.
because this is it's like a new age. All these things that are coming out now, it's unimaginable to us. Like in my childhood,
Yeah.
who would have ever thought this? And there's so much more cool stuff that's being learned all the time. Well, Frank, thank you so much. Unless anyone
Thank
else,
you.
Anne, did you have a question, or Margaret?
Oh, are you asking me?
Yeah.
The only thing is, are there any just books that you can recommend to sort of, even if they're at the elementary level,
Yeah.
give us some grounding in the thoughts that some of the ideas and issues you presented?
There's a book I'm reading right now. In fact, it's very accessible. I don't have it up here on my desk, otherwise I'd hold it up on the screen for you. But it's by an astrophysicist, a woman astrophysicist, who by the name of Katie Mack, M-A-C-K, Katie Mack. And what the heck's the name of the book? It's the End of Everything, Astrophysically Speaking.
Oh, that's awesome.
And she talks about what the ultimate fate of the universe is. But before she tells us about what the universe's end is all about, the first couple of chapters go into a lot of detail about how the universe came to be the way it is, and how we know that it is that way. So she talks about the science and the findings, and and her writing style is very accessible. I think, and she's got a very delightful prose. It's just a fun book to read. So I can
Great.
send you the details on that as well.
Great. Thank
And
you.
it's a short book. I picked it up at Eagle Harbor Books a couple of weeks ago. So it's a good little starter. There are many other books as well, and I'll take a look at my bookshelf and pick a few out, and maybe send a reading list to Anne so she can share it with you.
And then we'll attach it to the video, and then people who are looking at the video in the future will be able to access that extra information too.
Yeah.
Well, Frank,
Yeah.
thank you so much. This is fascinating. I'm really excited. I remember when the observatory got reclaimed and started to be rebuilt, right? They were going to tear it all down, right?
Yeah. Well, and I have one other thing to announce. I just was talking last night to our good friend Jerry Elfendahl.
Hmm.
I'm sure you all know Jerry.
Sure.
He has come across a video recording of Ed Ritchie giving a talk on some aspect of, I don't know, mathematics or science or something. Anyway, and that video recording is available. I'm going to figure out how I can get a copy of it. And we'll be probably in the near future, we're planning to have a showing of that video at the observatory.
Great.
We can see Ed Ritchie doing what he loves to do.
And maybe that could go on your website.
Yeah.
Yeah, cool. Well, thanks so much again, and we will have you back, and we'll all be out looking at the sky.
Yeah, you're
Bundled
quite
up,
welcome. And yeah, go out and look for the Big Dipper, and then
Right.
then it's all downhill from there. Get yourself a copy of Stellarium
Yeah.
or any iPhone app,
Yeah.
any or Android app that will help you find your way around the sky. And come out to the observatory, and we'll show you how to use them.
That's great offer. Thank you so much. All right, everybody.
Okay.
Take care. See you
Bye.
later.
Bye.